Hello, my name is Chris Turner. I'm a computer programmer, a GIS enthusiast, machine learning and AI modeler, and today I wanted to share a little bit about a project I'm working on as an AI resident with AppZiva. Most of my experience is in computer programming and computer vision and looking for targets and images, but I've been really eager to take on some new challenges with data analytics. And so in this project, we aim to predict customer happiness based on customer surveys. So let's take a quick closer look at the project and the details and the background and see what we are dealing with. Okay, so a little bit of background on the company. This is a startup in the logistics domain, and they are specifically delivering groceries. And they want to assess their customers' happiness or unhappiness to be able to take necessary actions and improve their business. So they sent out customer surveys asking six different questions. Question one, my order is delivered on time. Question two, contents of my order was as expected. Question three, I ordered everything I wanted. Question four, I paid a good price for my order. Question five, I am satisfied with my courier. And question six, the app makes ordering easy. So after learning about the problem we're trying to solve, we can now take a closer look at the data in the database. And to do this, I loaded the pandas library and used the shape command, which tells me that there's 126 rows and 7 columns in the database. Use the head command to look at the first 5 rows. Y is our target variable, which is binary. Zeros are ones. X1 through X5 are ordinal values 1 through 5 corresponding to the ratings of the survey questions. I then used the .info function to look at the basic info of the different rows and found out that they all have 126 non-null values, meaning there's no missing data in the database. The unique command from pandas tells me that all of the data in the database makes sense, meaning for all the features, all of the values are between 1 and 5 as they should be, and all the values for the Y column are either 0 or 1 as they should be. So we don't have to do any cleaning or changing or deleting of data. Then use the .describe command, and we can look at the mean of the different values and how the values are spread out in the interquartile range. Y has a 54% mean, which means there's just slightly more happy customers and unhappy customers. X1 had a mean value of 4.3, meaning that both groups rated X1 pretty high. X2 was rated very low at 2.5. X3, it was rated in the middle at 3.3. X4 is rated just above the middle at 3.74, as well as X5 at 3.6. And X6 was also rated very high at 4.25. Okay, now that we have the basic information about our data set, we can move on to doing some univariate analysis. And so for each of these tests, I'll just go over a couple of the plots, not all of them for all the features in the interest of time. But the first plot that I did was bar plots, and I broke the populations into total, unhappy, and happy bars. And so, for instance, X1, we can look here and see that that for X1, the unhappy customers seemed to vote 3 or 4 for their happiness level with my order was delivered on time. And then if we look at for 5, we can see that happy customers were far more likely. And this sort of flip-flop in that data makes it look like X1 might be a strong candidate to discriminate against the two. If we look more at feature X2, the contents of my order were as expected, we can see that the populations for the different ratings for X2 are very similar, and it seems like X2 might not be a strong candidate for being a good feature to discriminate against our two populations. So then I made box plots, and here we can see that I have box plots on top for the entire population, and then the bottom row I split the populations between unhappy 0 and happy 1. We can see that X1, X2, X3, and X4 have very similar box plots where the interquartile ranges are similar for unhappy and happy customers. For X5, the interquartile range between X3 and X5 was a little bit wider, meaning the distribution uh, was a little bit more spread out between voting 3, 4, and 5. And then for X6, we can see that the same thing for unhappy customers, the distribution is a little bit more spread out between 3, 4, and 5, indicating that X5 and X6 could be good features for discriminating against the two populations. So then I made these KDE plots, and they show distribution of density of votes. And here again, X1 pops out with a density peak at 5. It's very high, and if we look at the density curve for the unhappy population, it's a little more there's a little peak at 4 and then a smaller peak at 3, but the two distributions look very different. If we look down at the KDE plot for X4, we can see that both distributions look very similar. So X4 again pops out as a feature that might not be a very strong candidate for discriminating between happy and unhappy customers. So for each of these plots, I went through all of the features and kind of kept track of what features were strong, what features were weak, what features were moderate. And I tried to aggregate all of those results into a univariate analysis takeaway. And here I found that X1 and X5 were strong candidates, X3 and X6 were moderate candidates, X2 and X4 seemed to be weak candidates. So after univariate analysis, where we look at each variable independently, we are moving on to bivariate analysis, where we can compare how two variables relate to each other. And to do this, I created these three correlation matrices: the Pearson matrix, the Spearman matrix, and the Kendall matrix. And it turns out that they all three look very similar. So we'll just draw our attention to the Pearson matrix, and we can talk about some of the results there. In terms of the way X1 relates to Y, it seems to be the one with the highest correlation matrix value of 0.28, and that shows that X1 is probably the feature that correlates most to being able to decide whether a customer is happy or unhappy. It also shows that that features X5 and X6 show a moderate correlation, and then X3 shows a sort of weakly moderate correlation, and X2 and X4 show not much correlation at all, and that's consistent with a lot of our other tests. In terms of how some of the other features relate to each other, it looks like X5 and X1 has the highest score of 0.43, but really, if you're looking to rule out a feature or find features that are redundant and make a case for reducing a feature by looking at one of these charts, you need to have a higher correlation value than 0.43. So 0.43 is the highest, but it's not so high. We would probably need something closer to zero point 0.7 or higher to make a case for not using one or the other of those features based on this test. So after bivariate analysis, I moved on to multivariate analysis, where I used recursive feature elimination to rank all of the features in the data set by importance. And one of the good things about recursive feature elimination is that you use it with different model types. So I ran recursive feature elimination with several different model types, I think 10 different model types, and I got scores for the different features in the different model types, and some of them were very different. We won't go through all 10, but here I have two different types, I think a random forest classifier and logistic regression. They show, for random forest classifier, shows that X5 is the most important, along with X2 and X3. And then for logistic regression, it shows x1 is most important with x5 and well, x1 and x5 really are the most important. So the next step in the process was to use Python's lazy predict package to get some benchmark scores for different models and how they might be working with the different feature combinations that the research has pointed to thus far. So I made a data structure, a Python list of the different feature combinations that the research is pointing to, and we ran a loop through those combinations. And for every combination, we used Python lazy predicts run lazy classifier function, and we then took the top three scoring models for each feature combination and we stored those into a data frame and printed them out with the Python tabulate package to get an idea of what models are working best with every given feature combination. So after getting the feature combinations and the models that worked best with those combinations from Lazy Predict, it's time to start training some models and looking for the best model. So what I did was to take all of the features, x1 through x6, and use iter-tools to create every combination from two features to all six features together. And for every combination, we then ran a specific classifier type and we kept track of the scores. And then at the end, we returned the classifier that had the highest score. So this was interesting because I got to run this code over and over and over with the different classifiers to find the one that did the best. And the results here were a little bit different than the research pointed out to me. It was the extra trees classifier performed the best with an 89.47% accuracy. And it did it with the feature combination of X1, X3, X4, and X6, which actually turned out to not be one of the feature combinations that the research pointed to. So I thought that was interesting, and I'm not totally sure why that happened, but I'm glad I ran a loop through all the combinations and tested them all. So in terms of key findings and insights and recommendations for the company, we can talk about the best features in the model. X1 had to do with importance of on-time delivery, so we can talk about the logistics of the company and trying to ensure there are less and less late deliveries. Or we could talk about premium options for faster deliveries if it's feasible. We can talk about X3, which had to do with fulfillment of order needs. And for that, we could suggest that the company put some energy into enhancing inventory management. For X4, it had to do with perceived value of the products. So we could ask some more detailed questions in an expanded survey to get a better idea of how customers are perceiving prices at the company. And X6, which actually scored really high among happy and unhappy customers, we can suggest that they continue to put effort into making their app easy to use and order products. Now, X2 wasn't in the best features combination for the best model, but it scored very low between happy and unhappy customers. And I suspect that if we ask more detailed questions about the order contents that arrive when groceries are delivered, that we might find some better data and questions related to X2 might help us distinguish between unhappy and happy customers as well. The other thing that I would recommend is for them to remake how they score the target variable of happy and unhappy from a binary feature to an ordinal feature, and they have the customers rate their happiness from 1 through 5, and we can get a more detailed view of how unhappy or how happy the customers are, and this might lead to a better performing model overall. So thanks for listening to my project, and I will leave a link to the Medium article I wrote about this project, as well as a link to my LinkedIn page. Feel free to say hello anytime, and thank you very much.